The year 2038 problem is an issue for computing and data storage situations in which time values are stored or calculated as a signed 32-bit integer, and this number is interpreted as the number of seconds since 0 o'clock UTC on January 1, 1970. Such implementations cannot encode times after 3:14 and 7 seconds UTC on January 19, 2038, a problem analogous to the Y2K problem, or Millennium Bug, in which two-digit values representing the number of years since 1900 could not encode the year 2000 or later. Most 32-bit Unix-like systems store and manipulate time in this Unix time format, so the year 2038 problem is sometimes referred to by analogy as the Unix Millennium Bug. Technical cause: the furthest time that can be represented in the Unix time format is 3:14 and 7 seconds UTC on Tuesday 19 January 2038. Times beyond this moment will wrap around, and be stored internally as a negative number, which these systems will interpret as a date in December 13, 1901 rather than January 19, 2038. This is caused by integer overflow. The counter runs out of usable bits, increments the sign bit instead, and reports a maximally negative number. This is likely to cause problems for users of these systems due to erroneous calculations. Programs that work with future dates will begin to run into problems sooner. A program that works with dates 23 years in the future will have to be fixed no later than 2015, for example. Early problems: in May 2006, reports surfaced of an early manifestation of the Y2038 problem in the OWL server software. The software was designed with a kludge to handle a database request that should never time out. Rather than specifically handling this special case, the initial design simply specified an arbitrary timeout date in the future. The default configuration for the server specified that the request should time out after 1 billion seconds. 1 billion seconds after 9:27.28 p.m. on May 12, 2006 is beyond the 2038 cutoff date. Thus, after this time, the timeout calculation overflowed and returned a date that was actually in the past, causing the software to crash. When the problem was discovered, AOL server managers had to edit the configuration file and set the timeout to a lower value. Players of games or apps which are programmed to impose waiting periods are running into this problem when they attempt to work around the waiting period on devices which harbor the coding by manually setting their devices to a date past January 19, 2038. Vulnerable systems: embedded systems that use dates for either computation or diagnostic logging are most likely to be affected by the 2038 bug. Many transportation systems from flight to automobiles use embedded systems extensively. In automotive systems, this may include anti-lock braking system, electronic stability control, traction control and automatic four-wheel drive. Aircraft may use inertial guidance systems and GPS receivers. However, this does not imply that all these systems will suffer from the bug. Many such systems will not require access to dates. For those that do, those systems which only track the difference between times dates and not absolute times dates will, by the nature of the calculation, not experience a problem. This is the case for automotive diagnostics based on legislative standards such as CARB. Another major use of embedded systems is in communications devices, including cell phones and Internet appliances which rely on storing an accurate time and date and are increasingly based on Unix-like operating systems. For example, the bug makes some Android devices crash and not restart when the time is changed to that date. As of 2012, most embedded systems use 8-bit or 16-bit microprocessors, even as desktop systems are transitioning to 64-bit systems. Despite the modern 18-24-month generational update in computer systems technology, embedded systems are designed to last the lifetime of the machine in which they are a component. It is conceivable that some of these systems may still be in use in 2038. It may be impractical or, in some cases, impossible to upgrade the software running these systems, ultimately requiring replacement if 32-bit time T limitations are to be corrected. The use of 32-bit time T has also been encoded into some file formats, which means it can live on well beyond the life of the machines on which such file formats were originally supported. MySQL databases inbuilt functions like Unix timestamp will return 0 after 3:14 and 7 seconds UTC on January 19, 2038. Data structures with time problems. Many data structures in use today have 32-bit time representations embedded into their structure. A full list of these data structures is virtually impossible to derive, but there are well-known data structures that have the Unix time problem: file systems, binary file formats, databases, database query languages, like SQL that have Unix timestamp-like commands, COBOL systems of 1970s, 1990s vintage that have not been replaced by 2038 compliant systems, embedded factory, refinery control and monitoring subsystems, assorted medical devices, assorted military devices. Each one of these places where data structures using 32-bit time are in place has its own risks related to failure of the product to perform as designed. Real-time data structures with the 2038 problem. The Digital Video Broadcast System has a similar issue on April 22, 2038, when the 16 bits used to transmit modified Julian days used for electronic guide scheduling will restart from 0. The ETSIEN 300-368 specification mentions in Annex C that the provided MJD formulas are valid till February 28, 2100, but makes no mention of the limits imposed by the 16 bits used to transmit the resulting value. The rival ATSC system will have that issue after 2048 due to its use of signed 32-bit GPS seconds that begin from January 6, 1980. NTP timestamps. The Network Time Protocol has a related overflow issue, which manifests itself in 2036, rather than 2038. The 64-bit timestamps used by NTP consist of a 32-bit part for seconds and a 32-bit part for fractional second, giving NTP a timescale that rolls over every 232 seconds and a theoretical resolution of 2/32 seconds. NTP uses an epoch of January 1, 1900. The first rollover occurs in 2036, prior to the Unix year 2038 problem. Implementations should disambiguate NTP time using a knowledge of the approximate time from other sources. Since NTP only works with the differences between timestamps and never their absolute values, the wraparound is invisible as long as the timestamps are within 68 years of each other. This means that for NTP the rollover will be invisible for most running systems, since they will have the correct time to within a very small tolerance. However, systems that are starting up need to know the date within no more than 68 years. Given the large allowed error, it is not expected that this is too onerous a requirement. One suggested method is to set the clock to no earlier than the system build date. Many systems use a battery-powered hardware clock to avoid this problem. Even so, future versions of NTP may extend the time representation to 128 bits, 64 bits for the second and 64 bits for the fractional second. The current NTP4 format has support for era number and era offset, that when used properly should aid fixing date rollover issues. According to Mills, the 64-bit value for the fraction is enough to resolve the amount of time it takes a photon to pass an electron at the speed of light. The 64-bit second value is enough to provide unambiguous time representation until the universe goes dim. Solutions. There is no universal solution for the year 2038 problem. Any change to the definition of the time T data type would result in code compatibility problems in any application in which date and time representations are dependent on the nature of the signed 32-bit time T integer. For example, changing time T to an unsigned 32-bit integer, which would extend the range to the year 2106, would adversely affect programs that store, retrieve, or manipulate dates prior to 1970, as such dates are represented by negative numbers. Increasing the size of the time T type to 64-bit in an existing system would cause incompatible changes to the layout of structures and the binary interface of functions. There is also no universal solution for the issue with DVB and ATSC real-time transmitted dates due to issues with legacy receivers. Also, the issue has yet to be acknowledged or resolved by either organization. The only workaround would be to discontinue all time-related metadata services such as programming guides and automatic date synchronization after the affected dates. One possible option would be to create new table types for the affected part of the specifications and use ISO 8601 date strings rather than fixed integers as is used in ISO 9660 and ISO 13346 file systems. Most operating systems designed to run on 64-bit hardware already use signed 64-bit time t integers. Using a signed 64-bit value introduces a new wraparound date that is over 20 times greater than the estimated age of the universe, approximately 292 billion years from now, at 15:30 and 8 seconds on Sunday 4th December 292, 277,026,596. The ability to make computations on dates is limited by the fact that TM year uses assigned 32-bit int values starting at 1900 for the year. This limits the year to a maximum of 2,147,485,547. Starting with NetBSD version 6.0, the NetBSD operating system uses a 64-bit time t for both 32-bit and 64-bit architectures. Applications that were compiled for an older NetBSD release with 32-bit time t are supported via a binary compatibility layer, but such older applications will still suffer from the year 2038 problem. OpenBSD, since version 5.5, released in May 2014, also uses a 64-bit time t for both 32-bit and 64-bit architectures. In contrast to NetBSD, there is no binary compatibility layer. Therefore, applications expecting a 32-bit time t will, and applications using anything different from time t to store time values, may break. The X32 ABI for Linux also uses a 64-bit time t. Since it was a new environment, there was no need for special compatibility precautions. Alternative proposals have been made, such as storing either milliseconds or microseconds since then epoch in assigned 64-bit integer, providing a minimum range of 300,000 years. Other proposals for new time representations provide different precisions, ranges, and sizes, as well as solving other related problems, such as the handling of leap seconds. In particular, TAI-64 is an implementation of the TEMP's Atomic International Standard, the current international real-time standard for defining a second and frame of reference. See also, time formatting and storage bugs, Unix Millennium, notes. References. External links, entry in How Stuff Works, the Project 2038 Frequently Asked Questions, Critical Dates 2038, a 2038 Safe Replacement for Time H on 32-bit systems, Cluett, James. 2,147,483,647 €. The End of Time, Unix. Numberphil. Brady Hare and A.